So in this session, we are going to do one more revision on one more topic, quick revision and past papers. Okay. And if you have time, we'll move on to the next topic as well. You have altogether 5 topics. Now we have done revision on 2 topics and second paper questions. Okay. Right. So the next topic I want to take is transaction handling and then distributed databases. Maybe we can take those two because those are highly related. Okay. Uh, Right, so distributed database, sorry, transaction handling. First, I will do a quick revision using our node, then UCSC node, then past papers, okay? Uh, Concurrency and transaction handling. Okay. Right, so remember in transaction handling, there are some situations where, okay, let me take the PowerPoint. Right, so there are some situations where it involves maybe multiple updates, multiple divisions, sorry, multiple deletes, inserts. Uh, if one insert is success and the other one is not success, that is issue. That is business wise, that is illegal situation, right? So in that kind of a situation, either what we need is either success as a whole or nothing happened. Fail as a whole, no partial success, because partial success means we violate business rules. Say you reduce money from the account, but you have not added money to the other account. That's a dispute. Either you do it correctly or you do nothing. So there is the whole idea behind transaction handling. Transaction handling becomes more complicated when concurrency come into the picture. So that means we don't want to put them into a queue and do one by one. So then it will be very inefficient. Rather, we want to let those transactions happen as much as possible parallelly. At the same time, we don't want to prevent any conflicting situation. So that is why it's very complicated thing. Okay, right. So success as a whole or fail as a whole. So if it is success, we call it commit. If it is failed, intermediate session task, then we need to roll back the completed task also. Okay, so that is the whole idea behind. So there are 2 possibilities, either commit or rollback. So rollback means undo the previously done subtask. Okay. So the things become more complicated because of the concurrency and also recovery management. But recovery management is not in your syllabus. So therefore we did not cover that, but just remember that is also make things more complex. Okay. Right. So in transaction handling, all the database operations are subdivided into read and write. For example, insert is read and write, right? Select is just a read. Update is read and write. Delete is read and write. Okay. So why insert is a read and write? You read that block of the disk and insert your record to that block and then write it back, the new updated block. Update also the same. Delete also, you take that block where that record exists and delete that record and then write that block back. Only retrieve where you just take the relevant block or set of blocks and we don't need to update it. Okay. So read is, select is just read. But insert is read and write, update is read and write, delete is read and write. So when it comes to transactions, we need to preserve the atomic property, sorry, acid property. Acid stand for atomic, consistent, isolation, durability. Atomic means it must be success or fail as a whole. Atomic, your transaction is the smallest unit. Consistency means if the database is business rules wise consistent before the transaction, it must be consistent after the transaction also. Isolation means when things are happening parallelly, each transaction must be isolated from undesirable effects. Durability means once the transaction is success, it must be persistent. Right? And when it comes to the transaction handling, we need to look at what are the possible conflicts. It's not we, the database management system, do it, right? Actually, what we are learning is what the database management is doing. For us, it's just begin transaction, do your task and end transaction. It will be either rollback or commit. But we learn the theory behind that, or how the DBMS handle it. Okay. So possible conflicts happens when at least one operation is right. Right. At least one operation is right. Otherwise, it's not conflict. Read is not a conflict. But read, read, write, those are possible conflicts. Possible. And of course, it must be between two transactions. Within the transaction, there are no conflicts. Okay. Right. So these are the possible conflicts. You can see there's no read, but you have write, read, write, phantom. Phantom is a special case. Right. So write is called lost update. So one transaction writes something, say to a particular field, and the other transaction also write to the same field. So that means the previous value is now overwritten by the second transaction. Okay. So that is why we say lost update. The first update is now lost by the second update. So therefore that is not correct because initially both read the same value. Right. Ideally it should have been read this updated value and do it. Okay. Maybe you need to add some 100, so then it will be 1050 rather than 1100. If you read the, so that is the issue. Okay. So basically this update is lost. So those are possible issues. Write read is another one. After something is written, you read it. And then what happens if this rollback? So what if the second transaction read is wrong? Okay. Because this has been rolled back later. Right? There's no guarantee that transaction always commit. So then so if this transaction is already committed, this is even serious. Say this has written it, this has read it, and maybe change, and then this has committed, second one. Then only this one rolled back. So then this is irrecoverable situation. But if this is not yet committed, when this rollback, then of course, when this rollback, this must also be rolled back. That is called cascade rollback. So there are two possibilities for write read. Either it leads to cascade rollback or irrecoverable or unrecoverable transaction. So therefore, it's a possible issue. So then read write, unrepeatable read or incorrect summary or analysis problem. So that happens after one transaction read value, the other transaction write it, modify the same record. Now, if the first transaction again read it, it get a different value. Same transaction, when you read the value, you get two different values. That is called read write. So it results in inconsistency. Okay. So the phantom problem is first one read a particular data. In between, the other transaction has insert a record. And when second transaction read, it contains the new record as well. It happens when it is not, you are not reading one record, you are reading set of records. Right? So that is called phantom problem. Okay. So then we have isolation levels when it comes transaction handling. So either we need all perfect transaction handling or we can relax. Okay, we care about this, but we'll forget about the other thing. Right? So those are called isolation levels. So you can set the isolation level of the database before you start your transaction. So then that isolation level will be used for your transaction handling. So these are the isolation levels, right? Serializable is the highest level. So then no dirty read, no lost update, no non-repeatable reads, no phantom. Repeatable read is phantom can happen. Level 2. Level 1 read committed means phantom can happen, non-repeatable read can happen, even lost update can happen. But no dirty reads. Read uncommitted means anything can happen. Any of these issues can happen. So that means that is the weakest. Serializable is the highest. Okay. So you can set the isolation level before you start your transaction. Usually the by default you set it to serializable. Okay. Right. So the next subtopic we discussed was transaction schedules. So examiners have even asked what is a schedule list? Set of activities arranged in a time sequence manner. Okay. If that set of activities are related to a transaction, it's a transaction schedule. Like time ordered manner. So good transaction schedule will preserve the asset property of each and every transaction as well as it will speed up the process by do activities in parallel, not one after the other. One after the other is always perfect, but it makes very inefficient. Okay? Especially when we have thousands of users using the system at the same time. Right. So when it comes to transaction schedules, serial schedules are always valid. That means you don't make them the concurrent things. You finish one transaction, then another transaction, another transaction. Maybe first in, first out basis. Put it into a queue. So that is always safe, but at the same time, this is the most inefficient. Okay? Always safe, but most inefficient. So then we have serializable schedules. Serializable schedule means it's not a serial schedule, but that schedule is equivalent to one of the serial schedule. So therefore, it is safe. But at the same time, we do certain level of interleaving, mixing things to make it fast. So there are two types of serializable schedules: conflict serializable versus view serializable. So this is non-serializable. This is serial. This is conflict serializable, right? So every serial schedule is sorry. Uh, conflict serializable schedules are also safe. But BUP serializable schedules are also safe, but finding it whether it's conflict serializable is easier. So therefore, usually what we do is first check whether we can come up with a whether it's a conflict serializable schedule. If it is a conflict serializable schedule, that is perfectly okay. But if it is not a conflict serializable schedule, then ideally you must check whether it's a BU serializable. If so, still it is okay. Of course, serial schedules are always okay. Okay. But checking whether it's BU serializable is little bit more challenging than checking whether conflict serializable. Now remember there are two tasks. One is set up a serializable schedule. That is a hard problem. That is what actually the database management system does. But in your exam questions, what you get is they will give you a schedule and ask you to check whether it's serializable or it's valid. Right? Not asking you to build a serializable schedule. So there's a way to do building a serializable schedule, but it's not in your syllabus. It was in all syllabus when this subject is in semester 5, semester 6, but they have taken out that part when they take it to the semester 3. Okay, right. So therefore, you must know check whether a particular schedule is conflict serializable schedule. Okay, conflict serializable schedule. And also check whether it's a VU serializable schedule. Okay. So remember, serial transaction schedules are always safe, but not very efficient. So for example, if you have three transactions, there are factorial three number of possible transactions. T1, T2, T3, T1, T3, T2. That means you finish T2, then start and finish T1, and then so likewise there are six possible serial schedules. So all six are correct, valid. But these are the least performing schedules. Right. So this is an example. So this is your transaction one, this is transaction two. Read day at 100, write A. Read B at 100, write B. This transaction, it read day multiplied by 2, right? Read B multiplied by 2, right? Okay, right. So this is one possible serial transaction. You do T1 and then do T2. So this is another possible serial transaction. You first do T2 and then T1. Two different results. Sometimes you might wonder, okay, if there are two, if these are two different results, why do we say both are correct? Yes, it's two different results, but it is not our issue. It is not none of our issue, right? Both are valid. Okay. If you have any questions, you need to ask. Right? I can explain it again. Right. So anyway, those are serial schedules. Both are valid. But if you can create a schedule which is equivalent to either this schedule or that schedule with some overlapping, maybe we can come up with a conflict serializable schedule. Okay. So as I told you, creating a conflict serializable schedule is a hard problem, but verifying is very simple problem. So there are such kind of problems. We call them NP problems. Okay. Right. How do you check? Because how to create is not in your new syllabus. In your new syllabus, what you have is how to check whether a given schedule is conflict serializable. It's very easy. You need to first identify the possible conflicting operations, right? These are not conflicting, possible conflict, possible conflicting. What are possible conflicting operations? Two operations must be from different transactions. it must involve in the same data or same record. At least one action must be a write operation. Read, read is not conflicting. And then we prepare a precedence graph of dependency. And then we check whether there are cycles. If there are no cycles, it is serializable, conflict serializable to one of the serial graph. And we can check to which serial graph this is equivalent. Okay. Right. For simple precedence graph, how do you find the serial schedule? Start with one node and check if there is a path that travels all the nodes. So that path is the equivalent serial schedule. Okay. But there can be complex situations where you can't straight away find like that. Right. So then start with any node having in degree 0. That means for that node, there are no incoming uh, lines. And mark that. And remove all the outgoing arrows of that marked node. And now pick another node having in degree 0. And you keep doing this until all the nodes are covered. And that sequence is conflict serial schedule. Right? That sequence is the equivalent serial schedule. Okay. Right. So anyway, we have done these things. I'm just doing a quick revision, right? I think we took about 2-3 sessions to do this. Right. So this is a schedule. Read day, write day. Second one, this is transaction 1, transaction 2. Read day, write day. Time goes like this. Then read B, write B. Then read B, write B. Right. Right. So now you need to check whether there are possible conflicts. So I use the word very precisely, right? Possible conflicts. It must be between two transactions and at least one operation must be a write operation. This is same transaction. This is read and this is write. So therefore there's a dependency. Write and read, same data, two transactions. This is again write and write, but already we have taken that dependency. So this is new data, and this is between the in the same transaction because B is first time access. This is dependency. Write, read, same data. So write is also conflict, but we have already identified. So therefore, this is T1, T2. There's T1 to T2, T1 to T2, but no T2 to T1. So therefore, no cycles. So therefore, this is conflict serializable. Equivalent serial schedule is T1 comma T2. That means first T1, then T2. So if you do like this, the end results will be same as, right? Same as first you do T1 and then you do T2. Okay. So that results එකවර කරලා බලන්න පුළුවන්. මේකේ තියෙන අන්තිම result එකයි T1 කරලා T2 කරාම එකේ අන්තිම result එක අරන් බලන්න දෙකෙම එකමුත් results එන්නේ. ඒවා ඔයාලට කරන්න ඕන කුතුහලයක් තියෙනවා. Right. So this is another example we discuss. So read, write, same transaction, read day, write day, all defined. This is B, this is B, same. This is read, write, read, and this is again write, read, write. So therefore we have say T1 and T2. There's a dependency between T1 to T2 and also T2 to T1. So this is cycle. This is a cycle. So therefore this is not a complete serializable schedule. Okay.
So I didn't understand that cycle part.
What do you mean by that means you don't understand this as a cycle?
Yeah, can you explain it
This is a
again?
cycle, right? You can see you start from T1, go to T2, and again you come back to
That's
T1.
that solution part.
Solution means?
I understood how you got that solution. That cycle part I didn't understand properly.
That means identify whether there's a connection between T1 and T2.
Yeah.
So you can see here, okay, let me start from beginning. So you need to check whether there's a connection between these two, but you don't need to because this is same transaction. So possible conflicts are always between two different transactions, same data, and at least one operation must be right. So you need to use these three rules, and time goes like this. So this one and this one is not a conflict because same transaction. So then this one and this one, or this one and this one, yes, because this is not a conflict. Read is not a conflict, though it's two different transaction and same data. But write read is a conflict. Two different transactions, same data, one operation is at least one is right. So that means there's a dependency between T1 and T2. Right? T1 and T2 start. This is the first one, this is the next one. Time sequence wise, this is the later one. So then this is also possible thing, but we have already taken because right is conflict. Right, but already we have taken that. So no need to again show it. And this is new data. First time you access, so therefore no conflict. And this is same transaction. It's read write conflict, but not a conflict because it's in the same transaction. Conflicts are possible conflicts are different with different transfers. And this is a possible conflict because same data, B, two different transaction and at least one operation is right. So therefore there's a dependency between T2 and T2 to T1. Now what do we have cycles? This is possible thing, right. Two different transactions, same data. At least one is right. Actually here both are right, but already we have shown them. So now you can see there is the cycle T1 to T2 and T2 to T1. So therefore, this is not conflict serializable. Therefore, you can't tell what is the equivalent serial schedule because it doesn't make sense because this is not conflict serializable. Is it still not clear or still if you have very specific question, I can ask.
Understood, sir. Clear.
Okay, right. Right, so this is another example. So you need to do a lot of examples, past paper questions, okay, to understand this. Right, so this again transaction, read transaction 9 and 10, read X, sorry, okay, let's say read
Sir,
X, sorry,
which means if there exists a cycle, that means it is not conflict serializable.
no, if there's a cycle, it is not conflict serializable schedule.
Uh, then if there is no cycle, it is conflict serializable.
Yeah, that schedule is conflict serializable. And always
Okay.
you can find the equivalent serial schedule also.
Okay.
Okay, for example, this one, the equivalent serial schedule was T1 and then T2. T1 and then T2 because you can see it goes from T1 to T2. But here there's nothing called equivalent serial transaction because this is cycle. At least one cycle means it is not conflict serializable. Right, so what about this one? First of all, if the examiner gives the question in this format, you need to transfer it into this format. Right? Read text, write text, again read text, but by the other transaction. Write text, read Y, write Y, then again your T9 transaction, read Y, write Y. So once you put it into this format, it's easier. Now again, you need to check the dependencies. This is same transaction, not a possible conflict. But write and read, possible conflict. Within you don't have any conflicts. Okay. And first time you access Y, this is not a conflict because within the same transaction. And this is a possible conflict, write read. And again, this one is already taken, right? Right. So therefore, it goes from T9 to T10 and T10 to T9. So cycle exists. Okay. Cycle exists. Not serializable. So these are some more examples. Okay, some more examples. Right. So that is how you check. It's very easy. Once you understand, it's piece of cake actually. Right. How do you check whether a particular schedule is view serializable? Because maybe it's not config serializable, but it's view serializable. Right. So then what you need to check is there are three conditions. If these three conditions are satisfied, it can be view serializable if it is equivalent to a config serializable schedule. So that means your schedule is not config serializable, the given schedule. Right? If it is not config serializable, only we need to check whether it's view serializable. But it is, assume you find that it is view serializable to a different schedule, which is config serializable. So then this is also serializable because this is view serializable to this config serializable schedule. So therefore, this is also serializable. But these are two different schedules. Okay. So that is how you do it. Now, how do you check whether a particular schedule is view serializable to another schedule? And of course, that schedule must be config serializable. Otherwise, no point. This is view serializable to this one if this is not config serializable. But assume this is config serializable. Now, how do you check whether these two are view equivalent? Right. So you need to check three conditions. In those two schedules, initial reads must be done by same transaction. If in here the initially read is done by T3, here also it must be done by T3 for each and every data. And write read must be preserved. Here if there's a write and read, so first write by transaction 1 and then read by transaction 2. Here also that sequence must be preserved. Not other things, write read. And final writes must be done by the same transaction. If in this schedule, if the final write is done by transaction 2, here also final write must be done by transaction 2. So if these three conditions are satisfied, this is view equivalent to this one. Because we check with between these. And if this is config serializable, then this is also serializable. Because this is view equivalent to this, and this is conflict equivalent to serial schedule. So therefore, this is also equivalent to serial schedule. Right. So this is an example of two schedules which are view equivalent. T1, T2, T3, T1, T2, T3. Here we have only X data called X. So therefore, it's easy. So check whether which transaction does the initial read of X. T3 and T2 both. Initial read කියන්නේ එයාව වෙනස් කරන්න කලින් read කරන්න කවුද? T3 and ඒ දෙන්නගේ sequence එක වැදගත් නෑ. කවුද read කරන්නේ? Right? T2 and T3. Here in this schedule also T2 and T3. So that means initial reads are done by T2, T3. Here also T2 and T3. මේ දෙන්නගේ sequence එක වැදගත් නෑ. Whether it's first T2 or first T3. Okay. So then you need to check whether write, read sequence are preserved. Write, read. Here, X write, so T3 write and T1 read. T3 to T1 write, read. Here also you can say T3 write, T1 read. That write, read is preserved. And which transaction does the final write? Here T1. Here also T1. So therefore these two are view equivalent. Okay, view equivalent. Okay. මේක පොඩි කතන්දරයක් කියන්නේ. So therefore, if this is config serializable, this is also config serializable because this is view equivalent to this. And what is the equivalent serial schedule of this one? That is the equivalent serial schedule of this conflict equivalent schedule. Okay. Right. How to execute serializable schedules? So that is something that is not directly mentioned in your syllabus. So therefore, I just gave you a bit of a overview only. Right. So remember that this is after if someone has prepared the schedule, right? But in reality, no one is going to prepare the schedule, but the database management system need to prepare it by itself. So they need to when preparing a schedule, that schedule is actually prepared on the fly, run dynamically. Yeah, හරි. කවුරු මේ schedules එක ආවට පස්සේ prepare කරනවා නෙමෙයි. ඒ events වෙන අතරතුර මෙයා dynamically schedule එක restructure කරනවා. සමහර events පොඩ්ඩක් delay කරනවා. සමහර ඒවා කරන්න දෙනවා. ඒ delay කරන්නේ conflicts වෙන්න පුළුවන් දෙයක්. Okay. So it must preserve the serializability and also try to make it must make sure that it's not inefficient. So these are some techniques, log-based scheduling. Maybe you can remember these words, log-based scheduling, timestamp-based scheduling, optimistic concurrency control. ඔය තුනම තියුණා කලින් syllabus වල semester 6 යේදී දැන් නෑ. Okay. So in log-based scheduling, I'm not explaining you how it is done. I'm just giving you a little bit of an idea about that. Okay. So we log before a particular action is done. Say there's a write operation on a particular record. So database has a mechanism to lock that record. Lock means until the lock is released, other transaction cannot access that record. That is what is meant by lock. So lock is done at record level, not at table level. If you lock things in table level, that is very inefficient. එතකොට ඒ table එකේ lock එක යනකම් අනිත් ඒවා බලන් ඉන්නවා. Then lock කරන්නේ ඒ record එක. වෙන records වලට other transaction can going forward. Right? They can go forward. Right. So there are two type of locks. Read lock for the shared lock and write lock for the exclusive lock. So when transaction read a record, it needs to get the read lock, which is shared. That means multiple transaction can get that lock. But when a particular transaction need to write a particular record, it must acquire the write lock. And then only it can write the update it and then release the write lock. If you release කරන්නත් බෑ, there are rules, okay? ඒ ඔක්කොම අලුත් syllabus එකේ නෑ. The log based schedule දැන් මම කරන විදිය කිව්වේ නෑ හරි. කරන විදිය ඉතා දිග කතන්දරයක්. ඉස්සර ඒවයි questions එනවා දිග questions semester 6 වල. Right. So when you go for log based scheduling, there are two possible issues. Deadlocks and starvation or live lock. Okay. So I just gave you a bit of idea about what is deadlock is. So deadlock means basically මෙන්න මේ වගේ junction එකක වෙන සිද්ධියක් වගේ. A particular transaction has locked a particular resource and now it's waiting to say this transaction has locked this and it is waiting for this one which is already locked by another transaction. So first, in order to do the first task, it has locked this. But now it needs to do the second task, but it is locked by the other transaction. And now this transaction is waiting for this lock. But unfortunately, this transaction has locked it. And now this transaction is looking for this one. So usually locks are released after transaction is completed. But now this lock cannot be released because this is already locked by this one. And this guy cannot release this because it is waiting for this lock. So each two transactions are waiting for each other's locks. So therefore it's a deadlock. Right? Deadlock. So there
Sir,
are, yes,
in your example, you are showing the both the read locks, right?
both are
Read locks.
read locks.
So there's a shared lock, right? So what can be the problem with that?
Yeah, that is a good question actually. Those are shared locks. Yeah.
Sometimes because of one is read, another one is write.
Yeah, but
If
yeah,
that's so, if it writes, how it can write lock can be entered again because read is blocking that one.
no, your question is valid. Read is a shared lock. So therefore your question is why can't this guy take the lock, right? So that is a perfectly valid question. Actually, I never thought about this. Actually, this is not something I have created. You can see that I don't have this kind of uh, nice handwriting. I took this from some website or somewhere. Okay. But I didn't check that actually. But now also I feel like your point is valid because read locks are shared. So why can't even get this lock? Okay. Because read locks are shared, right? Yes, that's a valid point actually. Yeah, maybe this diagram should make more sense. Maybe if this is a right lock or something. Okay, right lock because read locks are actually shared. But if this is a right lock, so then yes, then this is deadlock, definitely deadlock. Okay, this is definitely deadlock.
But I have a doubt, sir.
Yeah,
If T1 lock the read, if it use the read lock, then T2 can't enter. So how we can use
what
the
do you
right
mean
lock?
by can't enter? Now remember T1
That's
has locked R1. Okay, resource one.
okay.
Okay, maybe this is not read, maybe resource. I don't know because this is not my image. So one possible now you thought that this is a read lock, right?
Yes,
But
sir.
I think whoever prepared this diagram, because it's not my diagram, maybe the idea is this is a resource one and resource two. Okay, so if that case, that means this is not referring to whether read lock or write lock, right? I feel like this is resource one, resource two. Okay, so that means transaction one has locked the resource one and it is waiting for resource two, right? But transaction two has locked resource two and it is waiting for resource one. It's locked.
But locks are used for the same record, isn't it?
Yes.
So how it can be resource one and resource two? They must be considered the same resource, right?
No, I think you have misunderstood this. Now transaction can involve multiple tasks, right? For example, this is transaction one. I think you have a little bit misunderstood the concept, right? We have the transaction also, right? But I think this is not the same transaction. So remember, say this is transaction one is working with A. It has log A, record A. Okay. Transaction one has log record A. Now the next step of the transaction one is do something to B. Right? That can do you agree that it can happen, right? You do something to A and then you do something to B record.
We can, sir.
Yeah. So then, but by that time, because things can happen in sort of a not parallel, part of transaction one, part of transaction and two, or something like. Say after transaction one log A, say transaction two has log B, B resource, so B record. Now transaction one try to log B because maybe that transaction, the second task is something to do with the B, but it's not yet released. At the same time, now transaction two second task is maybe next task or another task is something to do with A now. Now T2 is waiting for A, uh, release of the A block by T1, and T1 is waiting for the release of B resource be locked by T2, but both are looking at each other, right? So therefore, T1, because locks are released usually at the end of the transaction, right? But T1 cannot end its transaction, therefore it can't release this. T2 cannot finish its transaction, therefore it cannot release B. And each one is looking at the release of the other locks. Okay. So therefore, this will never happen. That is why we say deadlock. So in database management system, DBMS time to time check whether there are deadlocks. If log-based transaction is done, periodically check it and abort one of the transaction. So then this lock is released, then T2 can finish. T2 can finish because now it can get this block. And then T1 is restarted by the DBMS. Right? After delay, it will again, because it's rollback, now it will be again done. So the users will not feel what happens. User might feel a little bit of a delay, like a milliseconds, but at the end, both transactions are done. Because when you roll back a transaction, it can be re-performed in the DBMS. Is it clear now? I think this is resource one, resource two, right? Not
Now
main
I get
topic.
it, sir.
Yeah. Because it is not my diagram, I also got confused. Now I feel like this is resource one and resource two. Okay. Right. Right. So that is called deadlock. Another thing is starvation or live lock. That means one transaction is waiting for a lock to release, right? To continue its next operation. While it is waiting, another transaction, high priority transaction is also now waiting for the same resource. Now that high priority transaction get the lock. Now the other earlier guy is still waiting. And maybe another high priority transaction again looking for the same resource and it get it. Sometimes if this is a very busy database, a particular transaction may be waiting for very long time. So that is called live lock or starvation. Okay. So those things also DBMS must monitor and give those starving transactions a chance. Okay. So these are very rare but can happen. Okay. Because if it is a banking database or something, you can't let deadlock to happen, right? So that means customers have no idea what happened to their transactions. Okay. Right. So the second approach is, how to build the schedules on the fly, timestamp based management, transaction management, which is a different story. It doesn't use the concept of locking. It uses the concept of timestamps. But it's again long story. I don't want you guys to understand that, especially when the exams are nearing. Of course, if you have done that earlier, that is fine. But I don't see any possibility of examiner asking those things. Okay, but those were there in the previous syllabus in semester 6. But just be aware there's a log-based transaction handling mechanism, timestamp-based transaction handling mechanism, and also there's another transaction handling mechanism called optimistic approach. Okay. But we are not going to look at how it is really happened, how it is really done, okay, by the DBMSs. Okay. Right. So that is how transactions are handled in relational databases, right? Relational databases. Right, so we'll take a small break and then we'll go through the UCSC note. So the UCSC note has a bit of transaction handling in NoSQL databases also. So then we'll do the past paper question. I think we may have done the past paper questions, but we'll do another round of things, okay? Most of the stuff is covered in our discussion, right? So understand what transaction processing is, define properties of transactions, that is ACID properties, understand schedules and serializability, identify different type of serializability techniques, explain transaction support in SQL. That is set isolation level, begin transaction, and so on. And this one we have not covered in our note. Understand consistency in NoSQL databases. Okay. Right. So remember, the things are more complex when we have multi-user systems, right? Single-user system means like access. So those are personal databases. There's transaction handling is super simple, right? Because no parallel transactions. But Oracle, MySQL, those are multi-user systems. Multi-user means multiple users can access the database, multiple sessions, right? So we need to achieve interleave transaction because those are more efficient, right? More efficient. Interleave means bit of transaction one, bit of transaction two things, bit of transaction three things. So that is why we prefer serializable schedules rather than serial schedules. So transaction is the logical unit of database operation, smallest unit. That is why we say atomic. So if your transaction involves only read operation, that is very easy. Because read operation, if you have only read operation, that transaction is of all your transactions are read only, there's no conflicts at all. But even when you have read only transactions, maybe other transactions are doing right. So therefore, still your read only transaction need to be handled. Okay. Remember, read write. Though you read, someone else write, and again you read. Right. So you begin the transaction, do the read and write operations, and end the transaction. So your end results can be either commit or rollback. Of course, you commit, but just because you write your commit, it doesn't mean that it always commit. Maybe it's rollback. So therefore, better word is you end the transaction. DBMS will either commit or rollback. So this is partially committed. But if it is failed, it's terminated. That is rollback. Or else it is committed. Success. Right. So we discussed these kind of examples. Like what are the possible issues? Right. Possible issues. Right. Write issue. There is lost update. Right. Write read issue. Temporary update. That happens when it become rollback. Right. If it is not rollback, this is not issue, but you never know, right? That you can see temporary update and has not yet rolled back in the original value. Okay. So then temporary update or dirty read. Right. So you read the dirty value, but this guy roll back. So then this read value is wrong. So this may result in either cascade rollback or irrecoverable transaction. Okay. So when this is rollback, you need to also be rollback. That is cascade rollback. And of course, the incorrect summary issue. When you read two times, in between other transaction has written. Okay. Right. So each and every problem you need to understand. Okay. Between these two reads, you are reading the same data, but you get two different values. Because between reads, other transaction has write the same value. Right. So possible failures. But even computer can fail, right? Hardware. Right, acid property we discuss, okay? Atomicity, consistency, isolation, durability. So these are how do we do it, like log-based transaction handling. This is so that log-based mechanism effectively create a config serializable schedule. It's an interesting topic, but not in your syllabus. It's interesting and pretty challenging thing to understand also. Right. So isolation levels, level 0, level 1, level 2, level 3. So level 3 is the true isolation, serializable. So each level, which problem is resolved, which problems still exists. That is something you need to remember also. Like which problems are still like the way can happen, which problems are resolved. You can see UCSC note has a lot of focus on isolation level. So therefore pay a lot of attention to that. Maybe some practical examples for each level. So this is not something we discuss in our note, that is snapshot isolation. Right. So this is not level 1, level 2, level 3. It's a different isolation. So another kind of isolation was called snapshot, because examiner might ask this snapshot isolation, which is utilized in some common DBMSs. Several concurrency control techniques depend on this. So at the start of the transaction, it sees the data items that it reads based on the committed values of the items. In the database, that is a snapshot. Okay. So it look at only committed values. Okay. So due to this property, it ensures that the Python read problem doesn't occur, since the database transaction will only see records that were committed at the type of transaction start. Okay. Therefore, any insertion, deletion, update that occur after the starting of the transaction will not be seen by it. So it sees a very consistent view, because it doesn't consider uncommitted values. Okay. Uncommitted values. Right. Durability, the final isolate acid property. Right. So then what is serial schedule? What is config serializable schedule? What is view serializable schedule? Okay. So using precedence graph or dependency graph, how to check whether a particular transaction is config serializable and what is the equivalent serial schedule. Okay. So sometimes cascade rollback must be done, but some cases there can be the schedule, the way the schedule is committed, sometimes it's irrecoverable. Right, serial versus non-serial, and serial schedule can be config serializable, weave serializable, or true serial. And if you have any doubts, of course, you can ask those questions here, and also talk to ChatGPT. Ask your specific questions. Right. If you don't understand, ask another question. So chat AI agents are for the critical thinkers, right? Critical thinkers. It will keep giving you different examples and so on. Right. So use a precedence graph to check whether there are cycles. Right. So draw the precedence graph. Now this one has cycles. You can see this one, no cycles, right? There's a cycle. T1 to T2, T2 to T1. This is there's cycle. And also you can see there's another cycle. T1 to T2, T2 to T3, T3 to T1. This is again another cycle. This is a cycle, right? So this is a cycle. So therefore, this is not config serializable. It contains cycle. Right. So finally, the view equivalence. Okay, what are the three conditions? Okay, the three conditions. මෙයා ලියලා තියෙන හරි දරුණු විදියට ලියලා තියෙන. හරි මම ඔයගලන්ට ඉතාලම සරලව නෝට් එක හදලා දීලා තියෙනවා. මේවයි තියෙන ලොකු සීන් අයින් කරලා හරි සරල භාෂාවෙන්. Okay, see whether this is view equivalent. Initial reads, right? Initial reads are done by T1 for A. For B, here also initial reads is done by T1. What about B? Initial read is done by T1. Here also initial read done by T1. So that condition is satisfied. So then write read. So there's a write read T2 to T1 for A. Right? T2 to T1. Write read. Do we have the same thing here? No, right? So this is write done by T1. Write read. This is T1 to T2. This is T2 to T1. So therefore, write read is not satisfied. Final write, okay, right? Final write is done by T2. Final write is done by T2. Is this equivalent? This can't be equivalent, right? But this says P is serial schedule, therefore S is view serializable, right? P and S. Oh, right, read the button. Over. Let's get back to our note.
Right read, sir.
Right, right. So, but this is A and B, right? So it must be same data. Right read T1 to
So
T2.
below one is write B and read
Now
B.
this is right read T1 to T2. This is also right read T1 to T2, right? So that one is okay. Do we have another right read? Right read, but this is not a right read because A and B, two different data. So I can see only one right read issue here. Right
So another
read.
one,
Which one?
below one, write and read B.
This one?
No, below one. Yeah, that one.
Right, yes, right read, yeah. So you can see T1 to T2, there's a right read. What about here? B, yeah, that is also T1 to T2, right? Yeah, so that means it's preserved. So right reads are preserved. And final write is for B is done by T2. Here also B is done by T2. T1, A final write is done by T2. Here also final write is done by T2. So therefore, no issue. Right? No issue. So these two are view equivalent. If this is config serializable, this is also serializable because this is view serializable to this. And if this is config serializable, this is also serializable. Okay. Right. Transaction support in SQL. Right. So you can set it into different levels. right? Isolation level. මෙතන level කියන්නේ නැතුව කිය read uncommitted ඒ නම් වලින්ම පාවිච්චි කරලා තියෙනවා, right? Isolation level, read uncommitted, right? Read only, read write. I don't know what is these two. I think that is syntax. These are the standard values. Read uncommitted, read committed, repeatable, read, serializable. This is the default. This is where all the issues are handled. Okay. This is which problems are handled, which problems are not handled. Serializable, none of these issues are there. No dirty reads, no non-repeatable reads, no phantom reads. Here, all three issues are there. Okay, and so on. So set the transaction isolation level, begin your transaction, commit your transaction. ඔයා commit කරාට අනිවාර්යෙන් commit වෙනවා කියලා නීතියක් නැහැ හරි. But you want to commit, but in reality it may be commit to a rollback. Anyway, this is not a very good example because this is just a select statement, right? Right, some examples. So many examples given, okay? So that means with different isolation levels, they have given you, I think those are good examples. Right, so let's double check this table is consistent with our table. Right. Good. I think they have given this kind of questions like the below. Okay, let's look at our note also. Because once there was a small mismatch, particular student mentioned it, but I don't know whether I fixed that. Is it the same? Of course, serializable, none of the issues happens. Repeatable read, phantom can happen. Repeatable read, yeah, phantom can happen. මේක හරි කියන්නේ වෙන්න පුළුවන් හරි මේක හරි කියන්නේ නරකයි ඇත්තටම හරි. Because serializable is the best. No, all are red. Red means actually all are nothing bad happen. These bad things happen or not. So in repeatable read, still phantom can happen, right? දැන් මම කොළ පාට කියලා දාලා තින්නේ examine UCSC note එකේ රතු පාටට තියෙන ටිකට හරි. Right, read committed, only dirty reads doesn't happen, right? Repeatable read, මෙතන පොඩි වෙනසක් තියෙනවානේ. Yeah, repeatable read only phantom can happen, correct? Read committed, lost update, non-repeatable read, phantom, those things can happen. මෙයාගේ තියෙන තුනයි නේද? Dirty read, non-repeatable read විතරයි අරන් තියෙන්නේ ඔයාගේ UCSC note එකේ. Dirty reads, non-repeatable reads. Your UCSC note has not considered lost update. Okay, but anyway, in repeatable read, read committed, dirty reads can happen. Dirty reads can happen, okay? Right, read committed, dirty reads can happen. Dirty reads doesn't happen. Read committed, dirty read doesn't happen, but other things can happen. In read uncommitted, all these issues can happen, right? In your UCSC note, they have not taken the lost update, WW issue. Right? ඒක consider කරන්නේ නැතුව තමයි table එක හදලා තියෙන්නේ. So therefore, maybe you can refer to the UCSC note. That means you can ignore the lost update issue. Okay. Right. Up in the other example, read uncommitted. Read uncommitted means any of these issues can happen. Okay. That is phantom, that is insertion in between, non-repeatable read. When you read 2 times, you get 2 different values. And dirty reads, that means you read uncommitted values written by another transaction. So therefore, if that transaction roll back, your read is wrong. That is called dirty read. Dirty කියන්නේ වෙන කෙනෙක් update කරපු එකක් ඔයා read කරන්න. හැබැයි එයා තාම commit කරලා නැහැ. ඒකයි dirty කියන්නේ. එයා roll back වුණොත් එයා read කරපු එක වැරදි. මෙතන දෙපාරක් read කරනකොට දෙවෙනි පාර එන්නේ වෙන value එකක්. මෙතන දෙවෙනි පාර access කරද්දි තව record එකක් insert කරා. එතකොට ඔයාගේ දෙවෙනි පාර read දෙකේ summary එහෙම වැරදි. Right, so read uncommitted means anything can happen. All these can happen, right? So let's read, declare that transaction can read rows that have been modified by other transactions. That is what is your read uncommitted. But you're not, this results in dirty reads, non-repeatable reads, and phantom, yes. You want their pen. Okay. So you can say isolation level, read uncommitted. Right, read uncommitted means this. Right, isolation level is set to read uncommitted. So then you are doing a select query in the transaction. We got the output as 49,000 as the result of the transaction T2. Okay, so this is T2. So it says we got the balance as 49,000. Okay. However, the actual balance should be 50,000 since T1 is rolled back to the original value. So the T1 thing. Right. So you can see this is a dirty read. Right. So I think this is a practical example, right? So T2 is doing a dirty read. This balance has been updated by T1, which T2 read. Select and you can see that T1 has rolled back. Because you read dirty values, that means you don't wait, T2 doesn't wait for this transaction to complete, rollback or commit. So therefore, now you are in trouble. T2 is not giving the correct answer. Right? So that is a practical example. That happened because your isolation level is read uncommitted. That means you can read uncommitted values. So likewise, maybe they will ask you to explain what is the result, what happens, or justify this situation, why it's happened like that. So then read committed. Earlier, read uncommitted. So what is the next level? Read committed. So that means you don't do dirty reads. Right? You don't do dirty read. That means you don't read dirty values, uncommitted things, but still non-repeatable read issues, phantom issues can happen. Okay. So that means you read only values which are committed. Right. See whether there's an example. So now read committed. Declare that the transaction can only read data has been committed. Okay, no dirty reads. Right, by another transaction. Thus prevent dirty reads. Okay, but can result in non-repeatable reads and phantom, yes. Non-repeatable reads and phantom can happen, but no dirty reads. So consider the following transaction T1 and T2 occurs on an account that holds 50,000. Transaction T1 reduced 1,000 from this. And then it is successfully committed and completed and committed. Then the transaction to read the value. Okay. And it read it twice. For some reason, it read it twice, maybe 2 reports. Okay. So now you can see this transaction. So this is actually dirty read, right? Before commit, you read it. So that means when you do that, inconsistent summary can happen. That is, if you read dirty values, you can see before commit, it has read 50,000, right? Maybe this time 49,000 because maybe though it's a commit, it may have been rolled back. Okay. Right. Suppose we have read committed. Right. Read committed. That is second isolation level. So there we get output 50,000 as the result at the first read and 49 as the second read. Because we have set isolation level to read committed, in T2, it's only reads committed data by other transactions. So read committed means you don't read uncommitted, non-committed data. Okay. Since T1 is not committed at the first time, T2 reads the balance. T2 reads the balance as 50,000. මනේ මන්ද කියන්නේ බයිල් වටාරමගේ තමයි explain කරලා නම් තියෙන්නේ. So repeatable read declares that statement cannot read data that has been modified but not yet committed. ඔය එක තමයි repeatable read කියන්නේ. It doesn't read uncommitted data. And no other transaction can modify the data that the current transaction has read until the current transaction has completed an additional data. So if transaction 1 has read a particular data, other transaction cannot update that data until this transaction commit. If it is repeatable read, right? So repeatable read level, right? Repeatable read level, only Phantom can happen. Only Phantom can happen. No dirty reads and no non-repeatable reads. And of course, serializable means all these issues are fixed. Even Phantom issue is fixed. Right? Serializable. Statement cannot read data that has been modified but not yet committed. No other transaction can modify the data that the current transaction has read. So this is non-repeatable read. It's repeatable read. This is uh, no dirty read. Committed කරපු නැතිව read කරන්නේ නැහැ. read කරපුවා update කරන්න දෙන්නේ නැහැ. හරි මෙන්න මේ කතන්දර දෙකම තියෙනවා. දෙකම තියෙනවා කියන්නේ serializable. Okay. So this is Phantom issue. You can see in between there's insert. So this is Phantom issue. Phantom issue. Right. Consistency, no SQL. Right. Remembering no SQL, it's a different phenomena, different philosophy. Right. In relational databases, it's very strict philosophy because the relational databases are for banking transactions, that kind of things. But NoSQL databases are more used for social media, right? Forums. So there the things are a little bit different, right? So there we are more interested in scalability, reliability, right? Rather than high accuracy. So in NoSQL databases, eventual consistency is preferred over immediate consistency. Eventual consistency means initially there can be inconsistency. Initially. But eventually it must be consistent. Okay. Update consistency. Update consistency in NoSQL make sure that write conflict doesn't occur. Okay. Write conflict doesn't occur. So there are two approaches for maintaining consistency: pessimistic approach, optimistic approach. The pessimistic approach prevent conflicts. Optimistic approach, optimistic means you are positive. That means you think that wrong things will not happen. That means you feel like 99% of the times things are going to be okay. Pessimistic means you think that most of the time things are not going to be okay. Right? So they are, in that case, best thing is prevent conflicts. But when you're optimistic, uh, you can just assume that no conflicts are there, but in case conflict, you resolve it. Resolve it. Okay. So I hope you can understand. Okay. Again, so if I give you a very simple example, දැන් ඔයා කොහේ හරි ගමනක් යනවා කැලේක. කවුරු හරි කියනවා ඕකේ හැමතිස්සෙම කූඩැල්ලෝ ඉන්නේ. ඒතර ඔයා මොකද කරන්නේ? බූට් දෙකක් දාගෙන එහෙම යනවා. ඇයි ඒ? You are pessimistic. You think that 90% of the time you are going to face that issue. So therefore your task is preventing. බූට් දාගෙන යනවා. But someone will say in a different jungle, එහෙම කූඩැල්ලෝ නැහැ. කලාතුරකින් එකෙක් ඉඳි. Now you are optimistic. So therefore now your task is detect and take actions, because you know that 99% of the time you are safe. Having boot is overhead, right? Right. So if you try to prevent, you call it safety, right? But if you let issues to happen and then quickly respond, this is called liveliness. It's same as pessimistic versus optimistic. So this is pessimistic, this is optimistic. Okay. This is pessimistic, this is optimistic. So optimistic means you think it's very rare, conflicts are very rare, but if it happens, I will handle it. Okay. Right, so this is pessimistic approach, prevent conflicts. More and more bright locks will be used. Okay, because you are pessimistic. But this is less performing, right? Because you are taking a lot of precautions. Right, so this is optimistic approach. Let the conflicts occur, but detect and take actions. Okay. So that means you're not locking these things, but still you check afterwards there's a conflict. Okay. Right. So these are different type of categories of consistency. Logical consistency ensure that different data items make sense together. Replication consistency ensure that same data item has the same value when read from different replicas. Remember, you can have different counts which need to synchronize frequently. Session consistency. Within user session, there is read your write consistency. Okay. That means you read your writes. Maybe others don't read your write yet, but you always read your write. Right? So you see the latest, but maybe your friends doesn't see the latest yet. So that is because consistency is only for your session. Right? So replications make things more complicated. Okay. Right. So this is one type of replication, master slave. Right? Master slave. So that means changes propagate to the slaves by master. So if there's a modification, you do it to the master. Master will propagate it to slave in clusters. So pros and cons can be easily scaled out if more read requests received. But if master fails, slaves can still handle the read request, suitable for read intensive systems. Okay. Right. Peer-to-peer replication, all the replicates have the equal weight. Every replica can process updates. Even if one replica fails, system can operate normally. Okay. Right. Cap theorem, ඒකත් කතා කරන්නේ. So it is when it comes to consistency, availability, and partition tolerance, you can't achieve all three. Right? You can't achieve all these three: consistency, availability, partition tolerance. So we can achieve only two. Only two. So these are possible situations: CP or CA or PA. Right? So that means you achieve C and P but compromise A. Achieve C and A but compromise P, or achieve P and A, you can compromise C. Okay. So CP, CA, AP. Right? Version stamps and so on. Right? We discussed those in that class. Right? මේවා ඉන්න අහලම නැහැ questions. මේ අගහරියෙන් අහලම නැහැ questions. හරි මට මතකෙද අහලම නැහැ. Right, so now let's see some past paper questions. Okay. අර අගහරිය පොඩ්ඩක් බලන්න recording එක බලන්න. මම explain කරා cap theorem එකේම. Now let's look at the past paper questions. We start from 2024. First, let's mark the questions so that we don't miss it. Right, so we have done 1A, 1B we have done. This is distributed database question. This one we can do now. Okay, let's use a different color. Right, so this one we can do. So this is distributed queries, okay? Right, so we can do this. We can do this. We can do this. We can do this. This is from topic 1. We can do that. Topic 1 again. On the question අපි දැක්කේ නැහැ on the question නැතිවිලා. So we can do this. මේක ඇවිල්ලා අතන data structures and algorithm question. Right. You can't do E because we have not done the right. On edit කරන්න පුළුවන්. අපි ඒක කරමු ටක් ගාලා. Right. So let's do the D1. Briefly explain peer-to-peer replication and master-slave replication. Remember in peer-to-peer, you do the updates to the peers. But in master-slave, you do update to the master and master propagate it to the slaves. Right? Slaves. Okay. So you need to explain that. Peer-to-peer replication, in this model, all nodes are equal weight. Equal weight means equal level, peers. And all replica can accept writes. මේ ඕන එකකට write ලියන්න පුළුවන් because there's nothing called master. Okay. So this eliminates the single point of failure because in master slave, master is the single point of failure. Okay. Master is the single point of failure. Let me delete this. Escape. Okay. Right. In master slave replication, primary or the master is responsible for all write operations. So we do write operations to the master only, not to the peers. And master is doing the propagation of update changes to the peers. Right? Updates are propagated to secondary or the slaves. Sorry, not peers, slaves, which can handle read operations, and slaves can only do read. Right? So slaves are used for reads. For write, you write the master, and master propagate the changes to slave. There can be some delays, but it will be more consistent because master will propagate to all the slaves at the same time. But in peer-to-peer, there can be inconsistencies because when particular peer is updated, when someone read that peer, you get the updated value. But when you read a different peer, it may not get the updated value because peer will take a little bit of time to propagate it to the other peers. Okay. Right. Second one. State one advantage and one disadvantage of peer-to-peer and master slave. Right? Straight from your note. So peer-to-peer, so there's no single point failure because there's nothing called master. Okay. Eliminate the single point of failures. So that results in better availability. So that is the advantage. Right? In peer-to-peer. But disadvantage is inconsistencies because when someone update peer 1, someone reading the peer 1 get the latest. But someone reading the peer 2 may not get the latest. That means they will say we got two different values. Right? Because peer will take a bit of time to propagate it to other peers. Okay. Straight from your note. Right. So we have another question, right? Yeah. 2A. Briefly explain interleaved process. Interleaved means you mix. Say you have two transactions, bit of T1, bit of T2, bit of T1, bit of T2. Right. So that is called interleaving. that make it more efficient. So if you don't interleave, the result is serial, one after the other. So that is perfect, but very inefficient. Okay. Right. Interleaving is processing technique where multiple tasks are executed by rapidly switching between them. Bit of T1, bit of T2, bit of T1, bit of T2. So this approach allows for efficient multitasking, efficient, but it's more complex, difficult to handle. There's a handling overhead. So therefore, people will feel like it's multitasking, but it's not actually real multitasking. Bit of one, bit of two, bit of one, bit of two. Okay. So parallel processing is different. Parallel processing is true parallel processing. Interleaving processing is sort of a pseudo parallel processing. So parallel processing means these things are processed parallelly, maybe by two processors, two clusters. Right. But in databases, it's more interleaved processing because in databases, parallel processing may not work because you need to keep track of the other transaction. You can't just do those parallel because one depends on the other. Right. So this is, I think maybe we have done it, but anyway, let's quickly do it. Consider the following schedule S2 executed using three transactions, T1, T2, T3. Note that each R1, W1 denotes read and write operations that belong to transaction Ti. Okay, right. So now we can prepare maybe we can rewrite it in a user-friendly manner, right? So this is transaction 1, transaction 2, transaction 3. Yeah. අපි lazy විදිහට හදාගමු. RX then R1 කියන්න ඕනේ නැහැ. මොකද T1 row එකේ තියෙන්නේ. WX then RZ then R2X R1Y මේව ලියාගත්ත ගමන් වැඩි ලේසි. R2Y R3 that means read by read this R2 read this write this then හරි ලේසි. Okay, now it's much easier. Is brain friendly. Visualization is easy. Right, so now let's see. This is same transaction. This is new data. This is write read. You can see read read is okay, but there's a write read. Right, T1 to T2. So then this is read Y. This is the first time Y is read. This is read. Read is not a conflict. Though it's two transactions, both are read. And this is again read, no issue because all are read. This is read dz. This is also read dz, read, no issue. This is also read, no issue. But there's a write. So this is read write issue. Okay, and again, this is read write issue. That means T1 to T3, T2 to T3, T1 to T3, T2 to T3. You can see there are no cycles, right? So there are no cycles because this guy coming this way. So therefore, this is config serializable schedule. It is equivalent to T1 to T2, T2 to T3. You can say T1, T2, T3 serial schedule. Right? T1, T2, T3 serial schedule. Right? No cycles, and it is equivalent to T1 to T2, T2 to T3. හරි ඔක්කොම කව වුණාම නවත්තන්න. අර ඉන්ඩිග්‍රී වයින් කර කර යන්න ඕනේ නැහැ මේක. This is a simple example. Right, any questions? Any questions? No questions? Right, good. If no questions, that is good, right? Perfectly understood. Right, second one. State whether the schedule S2 is view serializable. Justify your answer. අන්නේ මොකක්ද ඒක S2? Samanya view. So usually we check view serializability with another schedule, right? How can you say view serializable? Then you need another schedule, right? How do you say simply by looking at S2 whether it's view serializable? But that is a bit of a question for me. Because we can check whether two schedules are view serializable. One views equivalent with the other, but here we have only one. I don't know. Let's see what is the examiner's answer.
So maybe we can check the three conditions.
But we check the conditions in two schedules, right? So that in two schedules, initial read must be done by the same transaction, final write done by the same transaction, write read is preserved. But you need two schedules to check that. So how are you going to check the two conditions? So this is one schedule.
Yes, sir.
Yeah. Let's see what the examiner's answer. It's view serializable. Given schedule is conflicts. Yes. Right. So this is a very tricky question, and this is very frequently examined asked. Right. So I completely forget that. Now the question is, state whether the schedule S2 is view serializable. Remember, S2 is already conflict serializable. Right? Why? There are no cycles. If a schedule is conflict serializable, it is automatically view serializable. Why? Right? Remember the diagram I gave you? Subset. Where is it? Right, this one. Right, you can see that if a schedule is conflict serializable, so that is inside this. Right, you can see conflict serializable is inside view serializable. Right, so therefore, if a schedule is serial or conflict serializable, it's automatically view serializable. But there can be schedules which are not serial, which are not conflict serializable and still serial. So those are these schedules. So then you need to check whether this is view equivalent to a schedule here or here. But if it is a serial schedule or conflict serializable schedule, it's automatically view serializable because these are inside view serializable. Okay, so this is a very famous question, right? I think sometimes every other year examiner asks this. Even when this is in semester 6. Right? If a schedule is serial, it is automatically conflict serializable and view serializable. If a schedule is conflict serializable, it is automatically view serializable. But there can be schedules which are not conflict serializable, but it is view equivalent to a conflict serializable. So then that schedule is also view serializable. So therefore, there are three possibilities for view serializability. If it is serial schedule, it is view serializable. If it is conflict serial, it is view serializable. And there can be a schedule which is view equivalent to a conflict serializable schedule. Those are also view serializable. So that means your schedule can be here, your schedule can be here, or schedule can be here. But if the schedule is here, then it is not serializable. Is it clear? Actually, it's my I didn't read the question properly, or I was not very careful. Okay, right. So therefore, you don't need another schedule to compare. So you need another schedule to compare if your schedule is somewhere here. Then you compare it with another one here. Okay, and using those three conditions, and then this becomes realizable. Okay, I hope now you got it. Okay, so actually I made the mess of that. Yeah, so this answer is perfectly correct. Right, so that's it for that year, right? Yeah, that's it. Uh, so what about 2023? So at the end of taking all the sessions, we will take a 1 day session, okay? Maybe 2-3 hour session, because MCQ you have only 20 question, right? අපිට එක session එකකින් ඔක්කොම MCQ ටික කරමු. Right, so this is 2023. ඉස්සර mark කරමු. Right, we discussed this in the morning session. Yeah, 2A we can do, 2B we can do, 2C we can do, we should be able to do. This is, yeah, this is a calculation for indexing, right? Yeah, indexing. That you can't do. Yeah, this you can't do. Okay. So shall we do this? Right, so let's read it. Briefly explain two possible reasons for transaction to fail in the middle of the execution. Remember the UCSC note mentioned so many reasons, right? Using about 4-5 slides. Hardware failure, operating system failure, right? Maybe error in the database, or maybe resource conflict, like log conflicts, like a deadlock or something like that. Okay. Right, computer failure, transaction or system errors, right? Anything. Right, B part. Consider the transactions T1 and T2 given below and identify the problem that could occur if T1 fails. That means T1 rollback. When performing the operations, read the item total seed price. Read the item total seed price. Total seed price. Where is that? Read the item. Do we have here? No, it must be. No. Read item. I want
Last one of the T1.
yes. Read the item total seed price. So this one, right? Yes. So now T1 fails. That means when T1 is about to do this, T1 fails. That means rollback. It rolled back at this point, right? It rolled back at this point. By that time, these things have done. These things have done. Okay. Let's see what happens now. So this is basically you roll back, right? You roll back. If there's a dirty read here, now you are in trouble because this is rollback. All these right values are now wrong. So you can see there's a read. Right total seat price is now written. Available seats are also written. Now, are there any dirty reads? Yes, this guy read the available seats. Available seats. So that is a dirty read. Now, actually, this available seat is wrong because this transaction rollback. You need to explain that. Okay. Uh, Total seat price, what happens? This one also doing calculating the total seat price. Okay. Total seat price, but based on seat price, no issue, right? Seat price is only read by this transaction, not right. That is fine. Selected seats are again only read, not written. So therefore, this is fine. This is fine. Total seat price is fine. Okay. That calculation is fine because these things are not written by this. Okay. So therefore, this is not right in total seat price, right? So this is not read in total seat price. This is independently calculate the total seat price. Okay. So therefore, this is still not an issue, right? No issue, no issue, because this is available seats is this is an issue, but do they use available seats? Yeah, they use, right, to calculate new available seats, and then you write it, right? So therefore, this is the issue, right? To calculate, uh, now you can see available seats are written after doing modifications, but that available seats you read, right? No, you don't read, right? Yeah, you also read, but after this, but this is now wrong because this is rollback. So therefore, your calculation of available seat is wrong now, and you write it. So you need to explain that, right? So the conflict is reading of this available seat because this is after doing some calculation they have updated, but that update is wrong because this guy has reduced the available seat by selected seat, but actually those selected seats are now not valid. So therefore, this is wrong. This is wrong. Right? You need to explain. Yeah, it's a temporary update or dirty read. Dirty read issue. Dirty read issue is based on available seats. Okay, available seats. Okay? Because this is now rollback. So therefore, this transaction must also be rolled back now. Right? Make a rollback. Kuna can make a rollback around. Okay? Right. So you should be able to explain it. Okay, perfectly. You should be able to explain it. But make sure you only explain the point, right? Right. You can't say there's an issue with total seat price, right? Yes, total seat price is ultimately affected, but the real issue is reading these available seats, which is already dirty. Okay. And you use that to calculate available seats. Okay. Uh, I think this one is perfectly okay. Total seat price is not issue, right? The issue is available seats. Okay. Right. C part. So they have already given the precedence graph, it looks. No, this is the answer, right? Sorry. I thought this is the best part of the question. Let me make it smaller. Right. Consider the following schedule created using three transactions T1, T2, T3. So let's write it in the way we like. T1, T2, T3. Read day, write day. Sorry, read day. Sorry. Read day. write A, read B, read B, write B by third transaction, write B, second transaction, and write A, first transaction. Second transaction, third transaction. Right, so let's draw the precedence graph. This is read, no issue. This is same transaction, but there's a read, write, okay? Read, issue. You write something T1 reads. This is B, first time you read it. This is read, but this is read, okay, read. And this is write. And this is write A. A is not touch here. Write. Okay. Right. So therefore we have T1, T2, T3. T1 to T2. T2 to T1. That means definitely cycles are there. And of course T2 to T3 and T3 to T2. So 2 cycles. And also there's cycle like this also. Okay. Everywhere cycles. So this is not complete serialized. But you can see there you have cycle, there you have cycles. Right. So then that's it. It has 2 cycles. Right. So is that all? No more. Yeah, that's all right. We can do this one, right? Object databases. Right. So we can do that because we did that part in the morning. Explain the term polymorphism related to object database concept using suitable example. So remember polymorphism you can take as method overriding, overloading, or overriding, right? So that means your operations can take many forms, right? Either over, that is the සිංගිති විදිය තමයි මොකද්ද? Function or method overloading. Same name, different signature. So then the correct method is called. That is within the same class or even class hierarchy. But method overriding is same method name, same signature, but your super type has one implementation, subtype has another implementation. So then the correct version is called, right? Correct version is called. If it is super type object, the super type version is called. Subtype object, is, version of the method is or overridden version is called. So you need to explain that, right? The object-oriented concept of presenting one operation multiple form is known as polymorphism. For example, operator calculate area. This is the example, right? Calculate area can be calculating area for circle in 5r squared. Uh, both are say subclasses of shape class because it's using an example, right? Suitable examples. So then rectangle, you override the calc area method, but this time you multiply length and width. Same example that was given in your note. Okay. So this is override polymorphism. Maybe you can explain both because you're not explain both. Overloading polymorphism and overriding polymorphism. Okay. Right. So that's it. Then paper එකෙන් භාගයක් විතර ඉවරයිනේ. Right, so let's look at the other paper also. 2022. ඕගොල්ලෝ දිගටම පල්ලෙහාට යන්න. මේ all syllabus එකත් කරන්න. කරන්න පුළුවන් ඒවා. කරන්න බැරිවත් ඇති හැබැයි. හැබැයි වාට 21 එකත් මම හිතන්නේ all syllabus නෙමෙයි. හරි. Therefore do 21 also, right? But I will look at 24, 23, 22. So let's mark which questions we can do. Right, we have done this. This is distributed databases, right? Take up karna head of data. Distributed. Lot of questions from distributed databases. Still distributed transactions. 2A, 2B, B1, B2. Right, so this is index calculation. We can do D. Remember optimistic approach, pessimistic approach. They have asked even about snapshot isolation. Right, so we can do this. Karo. Green one. Save it. Right, 2A. List and describe 4 properties of transactions. That is acid properties. Atomicity, consistency, isolation, durability. You need to explain, okay? List and describe. The atomicity, the smallest unit of success or failure is transaction. So there cannot be partial success of a transaction, right? Consistency. So your database must be consistent from business rules perspective at the end of each transaction, right? Isolation, parallel transactions must not see any undesirable effect of another transaction. That is why we prepare the schedule. Durability, at the end of the transaction, it must be persisted. All the committed transactions must be persisted to the storage. Right, you need to explain those. Right, consider T1, T2, T3, T4. Draw the precedence graph. Okay, let's draw it. This is T1, T2, T2, T3. T1, T2, T3, T4. T1. This is read. Time is now going down. Okay. Read, no issue. Say both are read. This is again read. This is write. So that means there's a read to write conflict, read to write conflict. Okay. T1 to T3, T2 to T3, T1 to T3, T2 to T3. Read time from top to bottom. This is first time Y is read. This is same transaction. This is write read. T4 to T3. T3 better. This is write. Read write conflict is there, right? Read write. But it's already considered. So then is it first time you access? Okay. But this is read write. T2 to T4. T2 to T4. T4 अभी पता करें ना देता T1, T2, T. This must be T4. Right? T4 to T3. And this is T2 to T4. T2 to T4. And this is Z again. This is okay, read, but this is read. T4 to T1. Do we have cycles? Go like, no. No cycles, right? Because there's no T1 to T2. Right? No cycles, right? No. Because this is also not a cycle, right? Because this is, yeah, no cycles. Okay. So this is my precedence graph. Right? No cycles. Look at T2 to T4 is there. මේ මෙතන දාලා තියෙනවා මොකද්ද මේකේ data එක කියලා. That is always good idea. Right? For example, now you can see ඔයගොල්ලෝ අනිවාර්යයෙන් කරන්න. For example, I mentioned here there's a right examiner සමහර අවුරුදු විතරයි දාලා තියෙන්නේ. නමුත් ඔයා දාන එක ඇඟට ගුණයි. Maybe examiner give marks. Right? So here you can see there's a conflict, possible conflict, read write T2 to T3. So there you can say it's X. The conflict is due to X. Right? That is what the examiner has done. Okay? So show that kind of a thing in everywhere. Okay. Make sure you do that. Okay. Right. So let's see T2 to T3. Yes, X. You can see. Anyway, it's not needed later, but it's always good. Right. So next part, state whether the schedule is serializable or not with explanation. This is serializable because there are no cycles. Right. Serializable. There are no cycles. Therefore, the above schedule is serializable. දැන් ඊළඟට ආයේ මොන serial schedule එකකටද equivalent කියලා. දැන් අහලා නැහැ ඒකනේ. අහලා නැහැ. Okay. ඒක අහලා නැහැ. Right. Can you find out to which serial schedule this is serializable? I will give you 3 minutes because it's very important. Can you come up with answer if the examiner asks, yes, if this is not serial, if it is serializable, state whether to which serial schedule this schedule is equivalent. Right. Take 2 or 3 minutes and tell me.
So are you asking serial schedule equivalent to serial schedule?
Sorry?
Are you asking equivalent to serial schedule?
No, now we know that this is conflict serializable, right? Because no cycles. So conflict serializable means it must be equivalent to a serial schedule. My question is to which serial schedule this particular schedule is equivalent. So the same question they asked in the previous paper also, right? We found.
So answer is T2 to T4, T4 to T1, T1 to T3.
Okay, let me write it again. Right, but what is the first one?
T2.
T2 then?
T4.
Then?
T1. T3.
T3, right. So I'll give 1 more minute for others to check that. So there's a easier way. If it works, that is fine. But if it doesn't work, you need to use the second approach, in-degree approach. So the easier way is you start from one node and see whether you can go to all the nodes, right? If you can reach all the nodes, That is that sequence is the equivalent serial schedule. Okay. Right. So this answer is correct because you can do it in an easier way if you have seen it. Right. For example, you start with T1, sorry, T2, then T2 you can go to T4. Right. T2 to T4. So then from T4 you can go to T1. From T1 you can go to T3. Now you have covered all the transaction, therefore you are done. Therefore you are done. Okay. So what is the other approach? If you don't see it, it's good that you saw it, but sometimes you may not see it in the exam. So then what is the systematic approach? You start with a node that has in degree 0. In degree 0 means there is no in arrow to that node. For example, T3 is not a starting point because there are in arrows. T1 is not a starting point, there's an in arrow. But T2, there are no in arrows. So therefore, T2 is a possible starting point. T4 is not a starting point because there's an in arrow. So therefore, your only starting point is T1, T2 because there are no in arrows. So therefore, you start there. Then මේ වගේ දැක්කේ නැත්නම් හරි. So therefore, you start there. So then you need to delete all the no arrows going from T2. So therefore, now because you have selected T2 because T2 has no in arrows. Now you need to delete arrows going from T2. Now again you check whether there's any transaction with no in arrows other than T2. So here there's in arrow 2. T1 there's in arrow, but T4 there is no in arrow, right? Now there's no in arrow, right? It's all going out. So therefore now you can write T2, sorry, T4, T4. Now you need to delete because you selected T4, any arrow going from T4. Right. So now again you need to find out the transaction which is not yet used. T2 and T4 are now used, but no in arrow. No in arrow is T1 because T3 has in arrow. So therefore you need to take that. So then you need to delete any arrow going from T1. And now T1 is already used. Now of course T3 has no in arrows. So T2, T4, T1, T3, T2, T4, T1, T3. Okay. So because that can be a possible question. So first check the first step method. If not, try this, use the second method. If there are no cycles, always there's a equivalent serial schedule. Okay, it's guaranteed. Okay. Right. So do we have any other questions, transactions here? Yes. Right. Describe the pessimistic approach and optimistic approach. The pessimistic approach means defensive approach or preventive approach where you try to prevent conflicts. Right? Optimistic approach means you're optimistic, so therefore let the issues happen, but you detect the issues and fix it, take actions. Okay. So pessimistic is preventive approach. Preventive approach. Optimistic is corrective approach. Okay, corrective approach. Corrective. Let the conflicts to occur, but then take actions, corrective actions. Okay, right. So examiner has even given you some examples. In preventive approach, you go for locks. For example, when you go to washroom, you lock the washroom, right? It's a preventive approach. Preventive approach. So that others can't enter into the washroom. So that is you take the locks, right locks. Right? Because right others need to take that lock. But you are not going to release the lock until you are done with your work. Okay. Right. So in optimistic approach, let the conflicts occur, but detect and take actions. Okay. So they have given example. I don't know exactly what is this conditional update. Client does an update. Client does an update. Check just before updating. Save both updates and mark as completes. Maybe this is something mentioned in your note. Okay, I don't understand this exact thing, but okay, maybe you can give this kind of example if this question is repeated again. Okay, right. Describe the snapshot isolation. Right. So you always work with a particular snapshot. Okay, snapshot එක කියන්නේ ඒ වෙලාවේ තියෙන situation එක. So at the start of the transaction, it sees the data item that is reads based on committed values. So that means at the beginning of the transaction, there are committed values, right? You only work with those values. Okay. So that is why we say it's a snapshot. Right? So whatever the snapshot at the beginning of your transaction, those values you consider, not anything else. Right? You don't take those dirty values afterwards. Okay. Right. So then they have given, you can see two select statements are there, but these select statements are doing select all from age greater than 40, age greater than 40. So the same query twice, but you are going to get multiple records. Right. And here in between, you can see there's an insert into the same table and two records, one age 31, that is not going to affect these queries because these queries are only interested in age greater than 40. So this is not going to affect. Right. So basically, this is not going to affect. This is not a panther for these queries, but this one, this is 45. 45 is greater than 40. So therefore, if you get 10 records, here you get 11 records. So that is panther. Right. In between, there's an insert. Right. In between, this is not inconsistent summary. That is the same record is updated. Same record you read twice is updated. That is read write. Right. But this is panther. This is when you read, this record is also included in the secondary. So that is called phantom issue. Right? Panther. Okay. Right. So that's it. Right. So we'll stop at this point. So now we have discussed three topics: evolution of databases, the triggers and constraints, transaction handling. So tomorrow morning session, we will look at distributed databases and then we will look at indexes. Indexes of චූටි කැලක් කරන්නත් තියෙනවා අපිට. ඒ කැලක් කරන්න ඕන. Right. We'll stop at this point, right? Thank you.
Sir, tomorrow we are having at 8 o'clock or 7
No, not 8 o'clock, 7 o'clock. Right. 7 to, because there's a power cut actually. That is why I wanted to start today, of course, for different reason. I will go as much as possible. If there's no power cut, maybe we can go out until 11, but maybe 10:30 until 10. But definitely we are going to start at 7. Okay, not 8. Okay, right.
Okay.